Hello. In this sequence, we're going to consider fluid flow in a single circular tube that's sort of aligned with the flow direction. We're going to use that to explain why we see a huge variation in flow speed within a sample of rock, but also why we see a big difference between the permeability of one rock and another. So in order to do that, we'll show straight away what it is we're talking about and what the relevant equations are. So what we're considering here is, as I've shown here, a single tube of radius r, and you can imagine that it's coming out of the plane of the board. Okay, so we want to know what the flow rate is in that tube. Now, for those of you who are familiar with the Navier-Stokes equation, it's quite a nice exercise because it can be solved. In fact, it turns out we can solve the steady-state Stokes equation, so there's no non-linear term, and we're going to ignore gravity. And we have what's called the Poisson law, in recognition of Poisson, who was the first to develop this and actually to do some experiments to show that it was valid. So the total flow rate, which I call Q, okay, is given by the expression that's shown there. That's the equation. Now, looks a bit Darcy law-like in that there's a relationship between flow and a pressure gradient. And it's inversely proportional to the fluid viscosity of mu term. But the interesting thing is that the total flow in the tube scales as the fourth power of radius, r to the fourth. Now, this isn't just some mathematical quirk that comes out of the equation. It means something physically. Now, let's give an analogy that most people, I hope, are familiar with. If we looked at electrical conductivity, imagine this was a wire. And we asked, well, what's the conductance of that wire? That would scale with area, or r squared. Why is that? Well, because if you imagine electrical potential, the current is carried by the electrons moving under that potential. The same potential, all the electrons are moving at the same speed. If I double the area of the wire, I have twice the number of electrons that are flowing, so I have twice the conductance. If I double the radius, the area goes up by a factor of 4, and of course then I have 4 times the conductance. So that's sort of obvious. But in fluid flow, it's r squared, it's area squared. If I double the radius, in fact, the conductance goes up by a factor of 16. Now, why is that? Now, this is illustrated here at the bottom. Here we have another tube, which does indeed have twice the radius. And the colours aren't as clear as maybe they should be, but what we know about flow is that at the solid surface, the velocity is 0. As you go away from the solid, the velocity increases. Now, the point here is, if you've got a little tube, you can't get far away from the surface. So the velocity within the tube is always quite low. If I make the tube larger, not only do I just have more area, obviously, but the velocities within the center of the tube are also larger. So what you find here is that the velocity, the average velocity, is proportional to area. And of course, you have a bigger area. So you have an area squared scaling, essentially a double area boost. And that's very significant for fluid flow. So remember now, if I got a larger tube, it's not just larger so it carries more flow, but the speeds within it are higher. And that's going to be quite significant in what we're going to talk about later. Now, let's consider how this relates to permeability. So the first thing is just to consider a bundle of tubes. So I've shown 4 of them, but we can imagine we've got lots and lots and lots of them in an array. So we have a bundle of tubes. They're all aligned in the flow direction, and they're some distance d apart. And each tube, remember, has a radius r. Okay, so let's ask the first question, which is, what is the porosity? Porosity is the fraction of the total volume of the rock that is void space, right? That is, in fact, basically the holes. Before I go any further, the symbol given to porosity is phi. It's a Greek letter, Unfortunately, for some reason, people see on Word what Bill Gates might consider you want to use and use the wrong symbol. It's just the Greek or the symbol version of F, nothing else. Right? There are lots of other Norwegian versions of O's that look vaguely similar, but I'm afraid it's a Greek F, nothing else. So what's the porosity? Well, if we consider a single tube, if we look here, a single tube, okay, that has an area, cross-sectional area of pi r squared, but it occupies an area of rock that's d squared. So in fact, the porosity is simply the ratio of that pi r squared over d squared. Don't worry about it seems to be area, because remember, this shape just propagates out of the plane of the screen. Okay, so it's the same everywhere. So you can imagine I take a unit length. Now I look at the cross-section, and those are the ratio of the areas. Okay. I've also written down, just for repeat, this quasi law, so we know the flow in each tube. But in Darcy's law, and I've got Darcy's law also written down here for reference. In Darcy's law, we look at the flow, the volume of fluid per unit area. Remember, that's just per unit area of the whole rock, not just of the voids, okay, the whole rock. So the flow rate per unit area is that capital Q divided by d squared. So if I take just a single tube, it has an effective area of rock d squared. So Q over d squared is just the expression we've just presented here, divided by d squared. Okay? So that's fine. But now what I'm going to do is I'm going to substitute in the porosity term. Okay? So the pi r squared and the d squared essentially disappear. And what I'm left with is that the flow rate is proportional to the porosity times now an r squared term. And of course, I've got my pressure gradient. So what about permeability? This is, in fact, a porous medium, a very simple one, a sort of Swiss cheese with these nicely aligned holes. Remember, I've ignored gravity, so don't get worried about the gravity term here. If we look at this, Q is minus K over mu grad P, and then I've got another expression for Q. So the mu goes, the grad P goes, and what's left behind is in fact my permeability. So my permeability is phi times r squared divided by 8. Okay. Now, that's a rather useful expression because it says if I have a typical pore size and I know the porosity, basically porosity times the square of the pore size gives me an estimate of permeability, really a rough estimate. And then there's this factor of 1 over 8. But actually, in general, when we look at real rocks, of course, they're not all nice uniform pores that go straight through. They have a very tortuous pathway. And in fact, the radius we're looking at here is normally the radius of the restriction through which the fluid must flow in order to get through the rock. So just in general, I'm not going to dwell on this. Roughly speaking, the permeability is about 1/100th of phi squared. Okay, just to give, as I said, an order of magnitude estimate. So let's now look about what this means if we do look inside a rock. So some of the previous videos have shown images in 3 dimensions of Ketton limestone. Ketton is a quarry limestone. It's actually used for sculptures. It's an oolithic limestone. So essentially it has these carbonate balls, and then the gaps between them are, by consolidated rock standards, relatively large. So if we look on the left, this is a 2-dimensional cross-section through a 3-dimensional image taken with X-rays. And you can see that we have these sort of ball-like structures that are about 0.5 millimeter across, and typical pore sizes that are going to be nearly a millimeter to, say, fractions of a millimeter. So we see that sort of typical pore size. But if we zoom in, we can see that there are grain fragments, and they're going to be smaller pores, but actually these ooliths themselves, these balls, are themselves porous. And they have pore sizes that are fractions of a micron. So what's shown on the right are, in fact, scanning electron microscope images. So they're taken with a different technique, where we sort of zoomed into the pore space. And we're looking here, actually, in the highest resolution image. Right? This is 10 microns. You can see here the balls themselves are contained of little grains at a sub-micron resolution. So if we measure the pore size distribution, and there are ways of doing this that I haven't discussed yet, but what we can see here, this is frequency against what's called a pore throat radius. It's actually a local restriction to flow, obviously, because that's what's going to govern the flow. we see that we have these larger pores, right, with radii that are a few tens of microns, so maybe as much as 100 microns across, okay? And then we have other ones here, this is in microns here, this is less than a tenth. So if we look at the difference here, it's 1, 2, 3 orders of magnitude of variation in pore size. Now, if we go back to the Poisson law with this fourth power, that's 12 orders of magnitude variation flow in the pores. So when we actually look at flow within the pore space, and a previous video looked at that, we see this enormous, absolutely fabulously large range of local flows. Right? And that's because typically in a piece of rock, we may see pore size variations of 1,000-fold or even sometimes more. So that explains why within a single small rock sample, you see a huge variation in flow speeds. But what about the rocks themselves? So here, what we have is a table, and this is an indicative table, don't sort of take it as being precise, of different materials with a typical grain or pore size. Actually, a grain size isn't really a pore size. The pore size is what matters. It's actually the gaps between the grains. Typical porosities, and just an order of magnitude, just a rough estimate of permeability. Of course, it's something we can measure from a flow experiment. Take a piece of rock, we can measure the flow rate and measure the pressure drop. So we can measure permeability. It's not a mysterious object that we don't otherwise understand. But if we're looking at, for instance, aquifers where drinking water may be stored relatively shallow depths, we're normally looking at typical pore sizes that are around about 100 microns. And we're looking at permeabilities in square meters that are greater than a Darcy. A Darcy is 10 to the minus 12, so we're looking at 10, 100, or maybe even 1,000 Darcys. When we go deeper underground, we go rather than drinking water aquifers that may be tens or maybe 100 meters subsurface. If we go down a few kilometers into well-consolidated sedimentary rock that we may have for reservoirs, these will be storage reservoirs for CO2 or hydrocarbon reservoirs. Sandstones and calcites, for instance, or carbonates, will typically have grain sizes, or pore sizes, sorry, that are around 10 microns, we've already said this, maybe down to 1 micron. Lower porosities as well. And we normally have permeabilities that are in the millidarcy range. So 1 millidarcy is 10 to the minus 15 square meters. That's the sort of lower limit of a ordinarily productive oil reservoir. So about 1 millidarcy to 1 darcy, that typical range is what we see deep underground. And then, however, we have materials that are much less, or clay, for instance, is formed of very small platelets. The typical pore size is a fraction of a micron. Okay, the porosity is quite high in a clay, but the permeability, therefore, is really very low. Okay, so we're looking at 10 to the minus 17 square meters. That's sort of 10 microdarcies. But when we come to shales, shale is very fine sediment. The typical pore sizes may be about 10 nanometers. So typically, shale is considered sort of impermeable rock. It's normally what seals in hydrocarbons, stopping from flowing further upwards to the surface. And their permeability is typically 10 to the minus 20 square meters, or maybe even lower. But interesting thing about shale is that some shales will contain organic material. So when they were first formed, first sedimented, they contained partially degraded shallow marine life, which is then the source rock for oil and gas. Now, normally what happens is this oil and gas is squeezed out of the shale, migrates upwards and collects actually more permeable rock. But unconventional shale oil and gas production is about producing the oil and gas directly from that source rock. And so it's very low permeability rock, but if it's fractured through hydraulic fracturing, or fracking as it's called nowadays, you can produce economic quantities. But the point here is, traditionally, certainly in hydrology, there was this idea of sort of labeling things. You know, this is permeable, or this is not very, this is impermeable. That's all not really very useful. There is a permeability. Virtually all rocks will have a permeability. It's just how big it is. And to dismiss things as impermeable can be a little bit of a mistake, as you see from unconventional oil and gas production. But the point here is the range. Most reservoirs, for instance, may contain some sandy layers or little regions that may be heavily fractured, so with pore spaces that are quite large and permeabilities that are Darcy. But there'll also be clays and shales present, typically, and so you may see 10 or more orders of magnitude variation in permeability. So if we look at a large body of rock, we have enormous variations in the permeability. So even if we look inside a little piece of rock, we see huge variations in flow speed. And then between one piece of rock that may be mainly clay and another piece of rock that's mainly sand, we're also going to see an enormous variation. And that's one thing that we really need to take into account when we consider flow in porous media. It's an extremely important concept that's going to govern how we try and understand and interpret what's happening on a large scale. Thank you very much.